All right, good morning. Today we are going to resume working with complex numbers. And again, we have at the foundation, we have the letter I, okay, which represents the square root of -1. And we also have I squared equal to -1. And again, complex numbers are also referred to as imaginary numbers, but I like to just stick with the term complex numbers because there are, once again, some real life applications and some of the hard sciences that happen to deal with complex numbers. And for what we have with complex numbers, again, we have the standard form of a complex number is a plus bi. And some things I do want to mention about complex numbers. Okay, if you're working with radicals that are even roots, or in this case, square roots of negative numbers, and you're looking at adding, multiplying, dividing, subtracting, okay, you want to write the terms that are presented as square roots of negatives along the lines of the letter I. Okay, so we have just a key rule of thumb. Okay. When operating with complex radicals, if they're not already expressed in terms of the letter I, I'll give you just some cases shortly. Okay, and just some items that we have. If I have, let's say, the square root, and we'll say we have the square root of -121, and we have plus the square root of -81. Okay, so I'm looking at the square roots of the opposite signs of numbers that are already perfect squares. So you have like -121. Now the square root of 121 is 11. Now that of -121, that is going to be 11i. And for the square root of -81, square root of 81 is 9. And that of -81 comes out to 9i. So we have 11i plus 9i. Okay, whereupon we have the sum at 20i. Okay. And let's say if we have a difference between radical terms, and I'm going to give somewhat a different display. If we have, let's say, the square root of, let's say we had the square root of -48 minus the square root of -300. Okay, so if I were to go ahead and express what I have in terms of the letter I, okay, so I have the square root of 48i, and we have minus the square root of 300i. Now, upon first glance, these do not look like radical terms in the complex domain. But once we look at reducing, okay, so for the square root of 48, not a perfect square number, but it is the multiple of perfect squares greater than 1. And the highest perfect square that would go into 48, that is going to be 16. And 16 would go into 48 3 times. And for the square root of 300, not a perfect square, but the highest perfect square that will go into it is 100. And so looking at what we have here, so you have the square root of 16, which is 4. And have times the square root of 3 times I. And we have the square root of 100 is 10. We have times the square root of 3 times I. Okay, and if you notice the inside numbers within the radical, we have the square root of 3, and both of those are also I terms. So we have like terms in the square root of 3i, and if we combine the coefficients, we have 4 minus 10, which is negative 6. So we have, for the difference between the square root of negative 48 and the square root of negative 300, okay, this will simplify to negative 6 times the square root of 3i. Okay. And again, you could also write this as negative 6i times the square root of 3. Okay. Now let's say that crossing over into the realm of multiplication, and this is where it is very easy to make careless mistakes. Okay, now for what we have in the case multiplying, and if we have, let's say, the square root of negative 9 and we have times, okay, the square root of negative 4. Okay, what you want to do here, it says when operating with complex radical terms, first expressed in terms of the letter I. Now we've got the square root of negative 9 times the square root of negative 4. And the reason I'm saying this is a type of problem where it's easy to commit a careless mistake is that we had the same radical, and automatically one might just multiply together. Negative 9 and negative 4, say, well, negative times negative is a positive, square root of 36, and the square root of a term cannot reduce to a negative constant, and so the result has to be 6. But here's the thing with complex radical terms. Okay, there's an added dimension involved, and if I express these terms already in terms of I, so the square root of negative 9, okay, so this will become 3i, and for the square root of negative 4, okay, this will be 2i, and if I multiply 3 times 2 is 6, I times I becomes I squared, and once again, I squared is equal to negative 1, so we have 6 times negative 1. So for the product of the square root of negative 9 and the square root of negative 4, this comes out to negative 6. And in terms of taking what we have with radicals, if I have, let's say, the square root of negative 16 over the square root of negative 25. Okay, so I have both numbers inside the square root are negative, so I can just go ahead and write in terms of I. So I have square root of negative 16 becomes 4i, that of negative 25 becomes 5i, and again, so you're going to have i's to cancel. I'm just sort of dragging this out so you have i's to cancel, and that will reduce to 4/5. Okay, and I think with the addition, subtraction, and the division, okay, the rule regarding in terms of expressing in terms of I is virtually automatic. Whereas I think with multiplication, it's probably the operation that is the least intuitive in terms of, and just automatically writing in terms of the letter I. Okay, because there is that potential for careless mistakes, where it's easy to get into the habit of multiplying terms that are in the same type of radical and combining together, say negative times negative is a positive, square root of positive is a positive. But since we have complex numbers to deal with, again, you have that added dimension where it's almost like a little bit of added work to express in terms of the variable I, whereas with the addition, subtraction, and division, I would say that it's more baked in, so to speak. Now, in the case of what we have in the problems, okay, on page 80, I had mentioned to look into, and we have in the case of number 13, okay, so we have taken the product of terms, okay, that are expressed as square roots of negatives. So here we have the square root of negative 10 times the square root of negative 5. Okay. And again, there is that tendency to go ahead and take the product of negative 10 and negative 5. But you have to remember, you want to go ahead and express in terms of the letter I. So we have the square root of 10 times I also we have with the square root of negative 5, so we have the square root of 5 times I. Now, with no negatives inside the radical, you can go ahead and multiply 10 and 5 together. So this will come out to the square root of 50 I squared. Okay. And for what we have here, now we have a reducible radical, and I squared is going to go to negative 1. Okay, now for the square root of 50, 50 not a perfect square, and the highest perfect square that will go into this is going to be 25. And the square root of 25 is 5. We have times the square root of 2 times negative 1. And at the step, we could have already displayed the final result, but here, 5 times the square root of 2, which is the reduced radical form of the square root of 50, and then you have times I squared, which is negative 1, and we have the final output in exact terms to be negative 5 times the square root of 2. Okay, now for what we have in the case of number 18, okay, so we have a rational expression. Okay, so we have the square root of negative 80 divided by, okay, the square root of 5. And there are different ways you can go about this, but I'm just going to go ahead and take out the letter I. So we have the square root of 80I. And we have over the square root of 5. And the square root of 80 we can reduce. And the square root of 16 times the square root of 5. And we have over I. Now the square root of 5, okay, there's no negative inside, so there is no letter I to pull out. And if you notice between the numerator and denominator, okay, so we had square root of 5 shared, and then we are down to the square root of 16 times I, and the square root of 16 is 4. And so for this ratio, okay, this is going to go to 4I. So this is one way you can go about this, and that is with the factoring. But again, you want to go ahead and factor out the letter I wherever we have the square roots of negatives involved. Okay, now in focusing once again on the standard form of a complex number, that is, you have in the A plus BI format, and we have for number 42, okay, we're looking at expressing in standard form what's going to result from taking the square of 10 minus 3i. Again, so for 10 minus 3i, quantity squared. Okay, so you're going to have 10 minus 3i times itself. And if I take the FOIL, okay, so you have first product, you have 10 times 10, which is 100. And then we have the outside and the inside products to each be at negative 30i. And for the last part, you have a negative times the negative is a positive. So you have plus 9 I squared. Okay, but now for what we have here, we have with I squared, so I squared is equal to negative 1. And so for what we're going to have in the follow through, okay, so you got 100. And the outside and inside products, they are identical, and they will combine to negative 60i. And for 9i squared, so this will go to 9 times negative 1. So we have 100 minus 60i minus 9. And just combining, so your A term is going to be 100 minus 9, which will go to 91. And your BI term, we're going to have the negative of 60i. And that will be the final result in this case. For what we have in the case of, let's see, not number 43, number 50. Okay, so we have for 50. Okay, now this is going to be a case of what we're going to have with what we refer to as complex conjugates. Okay, I'm going to discuss that in just a moment. So here we have the square root of 5 plus the square root of 7 times I. We have times quantity, so we have the square root of 5 minus, okay, the square root of 7 times I. Okay, and if I multiply together, okay, so for the first product, right now I'm just going to leave in radical terms. You have the square root of 5 times the square root of 5. Now this will go to 5, I'm just going to put the radical display. I'm just going to put on the radical display right now. So I have the square root of 5 times the square root of 5, that would be the square root of 25. And then we have the square root of 5 times the negative of the square root of 7i. So we have the negative of the square root of 35 times I. And the inside product, we have the square root of 7 times I times the square root of 5. So this will be positive square root of 35 times I. And we have with the last product, so we have positive times the negative is a negative. And we have square root of 49 I squared. And for what we have on display, so we have the square root of 25 goes to 5. And for negative and positive, square root of 35i. Now this set of terms will go out. And we have minus, okay, now we have the square root of 49 goes to 7. And once again, I squared is equal to negative 1. So we've got 5, negative 7 times negative 1 goes to positive 7. And we have 5 plus 7 is 12. And if I had to display in any other way, so you have a non-negligible A term only. The B term is negligible. And if this were to be expressed in any way just to show the BI term, this would be 12 plus 0i. And 0i is still 0. All right. Now, for what we have in the crossover, okay, so what we have with complex conjugates. And this last set that we dealt with, okay, that was multiplying conjugates. And for what we have in this particular case, right, so we're going to have say for a complex number that is in standard form, we're going to have that the conjugate of a plus bi is going to be a minus bi, okay, and it's going to be a two-way street, and you can say it the other way around. Okay, so the conjugate of a plus bi is a minus bi, and also have the conjugate of a minus bi is a plus bi. And let's say just taking as examples. Now, if you have a complex number and you're looking for the corresponding conjugates, and we'll just start out with something like 4 plus 3i. Okay, so you have addition, and what's going to happen here is that you're going to almost entirely keep the terms. Now your a value is fixed, a is at 4, and here we have plus 3i, and the conjugate is just going to be taking the opposite operation, which is going to be minus 3i. So the conjugate of 4 plus 3i is going to become 4 minus 3i. And if we have, let's say, negative 3 minus 6i, well, the conjugate in this case, right, so whatever the coefficient that does not contain the letter I, whatever is without the letter I, that's going to stay the same in the conjugate. So negative 3 remains fixed, and anything that consists of the variable I, we're going to take the opposite sign in the conjugate. So we have the conjugate of negative 3 minus 6i becomes negative 3 plus 6i. And if we have, let's say, just the number 17, okay, so you don't have the letter I attached. Okay, so a is represented by 17, and guess what? In the conjugate, 17 is locked in. Okay. Now, if we have something like negative 14i, okay, so you have an I term, and with conjugates will consist of opposite sign I terms. So if we have just negative 14i, we're going to have in the conjugate the opposite sign, which is going to be at 14i. And for what we have with conjugates, we have for the product of two conjugates, the product of two conjugates will result in a real constant. And just like another case in point, say if I have 4 plus 3i and 4 minus 3i, okay, so foiling out. Okay, so I have 4 times 4 is 16. Outside product, we have a negative 12i. Inside product is going to be a positive 12i. And the last product we have positive times the negative is a negative, and we have 9i squared. And again, we have the outside and the inside products to cancel. And so we have is equal to 16 minus 9. And again, I squared goes to negative 1. So we have 16 plus 9. And the result here is going to be 25. Okay, and think about conjugates, okay, is that in the case of fractions, okay, have complex number fractions. Can be converted if they're not already as such. But complex number fractions can be converted to a plus bi form. By using the conjugate of the denominator. And we'll have just kind of a case in point. See, we have a ratio. See, we have 2 over 3 plus I. And we're looking at writing in a plus bi form. Okay, so for what we have here, so you have 2 over 3 plus I. And in the case of the conjugate of the denominator, so you have the conjugate of 3 plus I is going to be 3 minus I. And in terms of how the conjugate is going to be used, okay, so we have 2 over 3 plus I. Okay, now we're not working with the least common denominator per se, but what I'm going to do here, I'm still multiplying this ratio by 1, and this will be in the form of the conjugate of the denominator divided by itself. Okay, so once we look at distributing the numerator and denominator terms, so you have 2 over the quantity of 3 minus I. Okay, so this is going to be 6 minus 2I. And again, just for the product of conjugates, we're just going to have one number. Okay, so you have 3 times 3 is 9. Now again, the outside and inside products are going to cancel each other. Okay, so here with the outside. Okay, so outside, okay, we'll have the subtraction of 3I. And the inside product we have 3I, and the last product we have negative I squared. Okay, so you have 6 minus 2I, and have 9 minus. Okay, now I squared is at negative 1, and subtraction of a negative will revert to addition of the positive. So we have 6 minus 2I. 9 minus negative 1 becomes 9 plus 1 again, which is going to be 10. And if I look at separating, so we're getting closer to the a plus bi form. So you got right now I have 6/10. And the following term we have negative 2/10 of I, and simplifying the ratio. So our official a plus bi form of 2 over 3 plus I, this will come down to 3/5. 3/5 minus 1/5 of I. Okay, and once again, now for the set of problems we have originating from page 80, and now for ratios, okay, and there are in the mix. Okay, we have for number 51. And we have for this fraction, okay, so we have 6 plus 2I over 3 minus I. And again, so you have for the conjugate of the denominator. So the conjugate, 3 minus I is 3 plus I. So we have for this ratio, okay, so 6 plus 2I all over 3 minus I. And multiplying the ratio by 1 in the form of the conjugate over itself. So we're looking at 3 plus I over itself. Okay, so we have with the FOIL, okay, so we have 6 over 3 is 18. We have outside part, we have plus 6I. Inside part, you have 2I times 3, another 6I. And then we have 2I times I, so this is going to be 2I squared. And again, we have sort of history to repeat, 3 minus and 3 plus I. Multiplying, so you have 9, and again, so you have plus 3I minus 3I to go out. And we have negative I squared. So for what we have in the numerator, okay, so you have 18, 6i and 6i will make 12i. Then we have plus 2i squared. Again, we have negative 1. You have 9 minus I squared, so you have 9 minus negative 1. And just narrowing it down. Okay, so we have 18 plus 12i minus 2. Again, 9 minus negative 1. Okay, so that's 9 plus 1. Okay, so you have 18 minus 2 is 16. So you have 16 plus 12i all over 10. And looking at splitting up what we have in the ratio. Okay, so we have 16 tenths. Plus 12 tenths of I. So we got the A plus BI format, and then we have upon completely simplifying. So you have 16 tenths. Okay, so this would be 8 fifths. And 12 tenths of I. This will go to 6 fifths of I. And that'll be the result for what we have in number 51. Now, in the case of what we have with 52, and for this ratio, so you have 5 plus I all over 4 minus I. And again, now we got a ratio of numbers, complex numbers in standard form, but now the fraction itself is not a standard complex number. So again, just working with the conjugate of the denominator. Okay, so the conjugate of 4 minus I is going to be 4 plus I. So in taking what we have here, so we have the quantity of 5 plus I all over 4 minus I. And if I multiply by 1 in the form of the conjugate over itself, and in this case we have 4 plus I over itself, and we have with distributed. Okay, so you have 5 times 4 is the first product, so you have 20. 5 times I, you have the outside part, you have 5I. Inside part, you have 4 times I. Last product right now we have I squared, which is going to change over to minus 1. And for what we have in the denominator, okay, so you're just going to have one number to abound. So you got 16. Outside, inside products cancel. With positive negative 4I. Then we have minus I squared. Now taking what we have at the moment. Okay, so you got 20. 5I plus 4I is going to be 9I. We have plus, and I squared we have at negative 1 in the denominator. Okay, so we have what's going to be 16 minus I squared. So I have 16 minus negative 1. And we have with the numbers, 20 plus negative 1 is 19. Plus 9I, 16 minus negative 1 becomes 17. And just splitting up, and there's no radical reduction that is needed. And so we have 19 17ths plus 9/17 of I. All right. So again, we have with complex number fractions, again, in terms of converting to the standard form, again, the most common pathway is taking the conjugate of the denominator and multiplying that fraction by 1 in the form of the denominator's conjugate divided by itself. Now, for what we have in the case of 55 and 56, now we have just standalone terms. There's no addition or subtraction in the numerator or denominator. And these might have a little bit of a feel of sort of going around your elbow to get to your thumb, so to speak, especially when there's simplifying involved. Okay, and we have, if we go with the same route, okay, so we have for 5 over 13i, okay, and the denominator is only 13i. So you have the conjugate of 13i, and again, that's going to be the opposite sign of the I term, so we have negative 13i. And so we have with this ratio, so 5 over 13i, and multiplying what we have here by the conjugate, negative 13i, over itself. So here we have 5 times negative 13i, so this will be a negative 65i. 13 times negative 13, that will be a negative 169. Now we have I squared. And for the denominators, I have negative 169. I squared we have at negative 1. So negative 65i, and we have over 169. Okay, now this ratio can be simplified because the greatest common factor is going to turn out to be the coefficient that was in the original denominator, which was 13. So if I factor 13 from both, yeah, so negative 65i is 13 times negative 5i, and 169, okay, it becomes 13 times 13. So we have the 13s to cancel. So we have for the final phase, okay, so this will come out to minus 5/13 of I. And if I had to express an A plus BI terms, like if I had to give this explicitly, so your A term would be negligible. So I would have 0 minus 5/13 of I. Okay, now for what we have in the case of 56, okay, so you have the ratio, so you have 6 over 7i. Okay, so with the denominator at 7i, we had the conjugate of 7i. It's going to be negative 7i. and taking what we have here. Okay, so multiplied by 1 in the form of the denominator's conjugate over itself. Okay, so we have negative 42i. 7 times negative 7 is negative 49. I squared. Okay, so we have negative 49 times negative 1. Okay, so we have in following through, okay, so we have negative 42i over 49, and we have the greatest common factor between the numerator and denominator. Okay, it's going to be 7. Okay, so 7 is kind of regurgitated just like 13 was moments ago. Okay, so here we have 7 times negative 6i all over 7 times 7. Okay, so here the 7s will go out, and then we have just for the standard a plus bi form. Okay, so have negative 6/7 of I. But again, if I had to specify a, well, there's no a term, but if I had to represent the void of the a term, this would be 0 minus 6/7 of I. Okay, now we've been working with modes of factoring and looking at solving equations, like solving quadratic equations like the zero product property, the square root property of equality, and the quadratic formula. And so far we've looked at those only in the domain of real numbers. But we can have equations where even using the same techniques as earlier will result as complex roots. And for what we have in the crossover. So for what we have for equations with complex roots, just to kind of kick things off. If we're looking at solving for x, okay, and let's say we have a statement, and let's say we have x squared plus 4 is equal to 0. Okay, so we have x squared plus 4 is equal to 0. Now, if I had x squared minus 4 equal to 0, I could factor a difference of squares. And I could factor something like x squared minus 4 into real integer coefficients. But in the case of a sum of squares, even in the case of x squared plus 4, I cannot factor. And one might be tempted to say that, well, you know, isn't the square root of x squared plus 4 like x plus 2? And of course the answer to that question is going to be no. And I'm just going to mention, like, if you thought of x plus 2 right away, for x plus 2 squared, remember, this is not going to result as just x squared plus 4, even though it will have those terms. But what you're going to have instead will be x squared, and you have plus 2x. So you had that middle element with 4x, which is not present in this equation. So in terms of solving for x, okay, what we do here is isolate the x squared upon taking 4 away from both sides. So we have the x squared is equal to negative 4. Now, in terms of crossing over to the stage, where we have the square root property of equality to arise. Okay, like your x squared is equal to p, and p happens to be negative 4. And if I go from x squared to x, I have is equal to plus or minus the square root of p, so I have x equal to plus or minus the square root of negative 4. So while the square root of 4 goes to 2, that of negative 4 goes to 2i. So we have for the solutions in x, we have plus or minus 2i okay. So we have both roots are in the complex number system. Okay. And let's say that if we have another case here, and let's say that if I have the quantity of x plus 1 squared plus 36 is equal to 1, okay, and okay, so if I get, say, the x plus 1 squared by itself, so I'm going to take 36 away from both sides. Okay, so we had the square of x plus 1 equal to negative 35. And again, so just going back to the terrain, here we have utilizing the square root property of equality. Okay, so I'm going to go from the square of x plus 1 to x plus 1. And have is equal to plus or minus the square root of negative 35. Okay, so I got x plus 1 in first order. And for plus or minus the square root of negative 35, so this will go to plus or minus the square root of 35 times I. And square root of 35, that portion cannot be reduced in radical terms. Okay, so we have for the solutions in x, so we get x by itself, and if I take 1 away from both sides, I'm just going to lay this out in terms of horizontal addition and subtractions. I have x plus 1 minus 1, and this newly formed constant, and we'll have on the other side in front of the radical terms. And so we have for x, okay, we have for the compact solution, we have x equal to negative 1 plus, as well as negative 1 minus, okay, the square root of 35 times I. And once again, you can itemize the results. They have negative 1 plus, the square root of 35 times I, and negative 1 minus the square root of 35 times I. Okay. And just an item here. Okay, so square root of 35, okay, that was a radical that could not be reduced. Let me give you just one here. Say for third case, if I have the x squared is equal to negative 20. Okay, so if I go from x squared to x, So I have x equal to plus or minus the square root of negative 20 and if I go ahead and take out the letter I, say I have x is going to be plus or minus, okay, the square root of 20i. Now 20, like 35, not a perfect square number, but unlike the square root of 35, the square root of 20 can be lowered. Okay, so for the square root of 20, okay, so we have with the highest perfect square divisible into 20. Okay, so that is going to be 4. So the square root of 4 times the square root of 5 so this will go to 2 times, okay, the square root of 5. So for what we have in x, okay, so you have x is equal to plus or minus. Again, from the square root of 20, I have 2 times, okay, the square root of 5, and I have times I. I can write the results separately, and if I have interaction or the operation of multiplication between the radical and I can shift the radical behind the I and have like 2i squared of 5 negative 2i squared of 5. So it can also be written in that particular layout, or even plus or minus 2i times the square root of 5. Okay. Now another special case where we have radicals that consist of complex roots. And give you one here. If I have, let's say, 7x squared, and let's say if I have 7x squared plus x, and we'll say that we have let's say we have 7x squared plus x plus 3 is equal to 0. Okay, now this trinomial cannot be factored. If you're to think of factoring by grouping, remember you'll be multiplying 7 and 3, and the product would be 21, and you'd be trying to find out what factors of 21 would add up to 1, and there's nothing in the real number system whose sum or difference will amount to 1. And okay, so in this case, all right, if we're looking at a solution, okay, one recourse is to use the quadratic formula. Okay, so we have a at 7, and from x, which we have as 1x, we have b is equal to 1. And we have that c is equal to 3. And if we go with the quadratic formula on this one, okay, so you have for negative b, so you have the negative of 1. We have plus or minus, okay, the square root. Okay, so b squared is 1 squared. We have minus 4 times a times c, so you have a is at 7, and c is at 3. You have all over 2a, so you have 2 times 7. Okay, so you have negative 1 plus or minus, okay, and just working with what we have inside the radical. So you have 1 squared is 1, negative 4 times 7 is negative 28, negative 28 times 3 is going to be a negative 84, and in the denominator, okay, so you have 14, and so we have negative 1 plus or minus the square root. Now 1 minus 84 is going to be negative 83. And what's going to happen here? So I'm going to have -1 plus or minus. Again, we have the square root of 83 times I. And 83 is a prime number, and 1 is the only perfect square that is divisible into 83. And so just taking what we have, we're going to have, and I'm just going to leave this in compact form. So we have, for the solutions, we're going to have -1 plus and -1 minus the square root of 83i all over 14. Okay. And I'll tell you what, in the case of looking at solving equations, say we have just for the next few moments. Okay, tell you what, in solving for x, let's see what we get for x squared plus 100 is equal to 0. And also, we'll say we have x minus 10 squared is equal to -250 and we'll say that we have in the mix and this one I think is going to have a radical reduction, but let's see what we get for 7x squared plus 4x plus 1 is equal to 0. If you're still working on these items, that's okay. But I'll tell you what, since we're getting a little bit pressed for time, okay, we'll go ahead and look at what we have in these three problems. Okay, so we have with x squared plus 100 equal to 0. Okay, so if I isolate the x squared term, again, just like x squared plus 4, we have a sum of squares. And again, the real number system, you cannot factor a sum of squares in terms of integer coefficients. So if I get the x squared by itself, upon taking 100 away from both sides, okay, so we have that x squared is equal to minus 100. And we have been following through, okay, so with the square root property of equality, and we have going from x squared to x, and we have is equal to plus or minus, okay, the square root of -100. And so for plus or minus the square root of -100, this will go to plus or minus 10i. Okay, so if you have a sum of perfect squares, okay, what's going to happen here is that you're going to have the solutions to be a couple here where we have to be additive inverses and with the numbers in the complex domain. Now, for what we have for second item, we have the square of x minus 10 is equal to -250. And if I go from the square of x minus 10 to just x minus 10, so we have plus or minus, okay, the square root of -250 and right now, so we have x minus 10 equal to plus or minus, okay, the square root of 250i and for this number, okay, so for the square root of 250, not a perfect square number, but it is the kind of number where its square root can be a reduced radical. So for the square root of 250, highest perfect square divisible into 250 is going to be 25. And so we have the square root of 25 times the square root of 10. And that is lowered to 5 times, okay, the square root of 10. Okay, so for what we have in the case of our equations, they have x minus 10. So this will become plus or minus 5 times, okay, the square root of 10 times I, and getting the x by itself. Okay, so I'm going to add 10 to both sides, and just to sort of signal that I'm going to have the constant that is moved in front of the radical set. Okay, so we're going to have in this layout, okay, so we have the x is going to be equal to 10 plus or minus 5 times the square root of 10i. And if I were to display what I have here in separate notation, so I'm going to have 10 plus 5 times the square root of 10i, and 10 minus 5 times the square root of 10 times I. Okay. Now for what we have in the case of the last of the trio, okay, so we have 7x squared plus 4x plus 1 is equal to 0. Okay, and so we have with this particular trinomial, again, if I have 7 times 1 is 7, there are no integer factors of 7 that will add up to 4. Okay, and so I'm looking at, once again, the reapplication of the quadratic formula. Okay, so I have a at 7, b at 4, and c equal to 1. So just filling in what we have now. So we have with x, again we have negative b plus or minus, okay, the square root of b squared minus 4ac all over 2a, and just looking at filling in. Okay, so we have with negative b, so we have negative 4 plus or minus, okay, and we have the square root. Now b squared we have at 4 squared, and got minus 4 ac, so you have minus 4 times 7 times 1. You have all over 2a, so this will be 2 times 7. So we have negative 4 plus or minus. Okay, we have the square root. 4 squared is 16. Negative 4 times 7 is negative 28. Negative 28 times 1 is still negative 28. And 2 times 7 is 14. And for what we have in the layout, now we have 16 minus 28. This will go to the square root of negative 12. And so we have here, we have the square root of 12 times I. And kind of like 250, okay, 12 is not a perfect square, but it can be such that it is the type of number that can be a reduced radical, okay, in the square root. So I had the square root of 12, so I had the square root of 4 times the square root of 3 times I. So I have 2 times, okay, the square root of 3i. So for what we're going to have in the mix, okay, so you have negative 4 plus or minus 2 times the square root of 3i all over 14. And if you notice, we have even valued leading coefficients. Okay, so what I'm going to do here, I can factor out 2 from both the numerator and denominator. Okay, so with the numerator, so you have, with 2 factored out, so I have 2 times. 2 are going to -4, -2 times, and 2 are going to plus or minus 2 times the square root of 3i, plus or minus square root of 3i times. And 14, we have 2 times 7. And we have upon reduction. Okay, so we have for the end results here, and I'm just going to leave in compact notation, so we're going to have -2 plus or minus, okay, the square root of 3 times I all over 7. All right, and there is, okay, so for this set of equations, we have exclusively complex numbers. Now, so far we've dealt with equations that if we had like conditionals among them, okay, we had exclusively real roots, and now we've had exclusively complex roots. And they're going to be those equations that will have a blend of both real and complex roots. And those will be, in large part, what we refer to as equations that will be quadratic in form. Okay. Now, just reminders we have with Alex homeworks. Okay, so you have the section R5 with the radical and absolute value equations that is due this evening. Again, class activity 1 through Alex, that is due Saturday, January the 30th. And the Alex homework in section R6 will be due Monday, and section R8 will be due Wednesday of next week. And again, I do have video simulations for sections R6 and R8 inside the weekly notes tab, and items to go ahead and be looking at. We have on page 81 numbers 57, 58, 61, 68, 71, 92, and also number 94.